Let us first turn to the probability that an accused individual is actually convicted by a 12-member jury. In notation, we want the probability of the event C. Now, naturally enough, we look to decompose the problem, and a natural partition is immediately suggested based upon whether the individual is guilty or innocent. And therefore, by conditioning on whether they are guilty or innocent, we can simply decompose the probability of conviction. Of course, the listener will recognize an appeal to the theorem of total probability. Additivity has come to the fore. The moment we write such an expression down, it now becomes almost transparent. The probability of guilt is just the probability that the indicator Z of guilt is 1. But if the person is guilty, then conviction occurs if the number of juror errors does not exceed 5. Jury decisions are independent of guilt or independence, and therefore now we have the first term. The probability that S12 doesn't exceed 5 times the probability of guilt. The second term, likewise, if the individual is innocent, then Z is 0. And if the individual is innocent, conviction occurs if and only if the number of juror errors is 7 or more. Again, jury decisions are independent of guilt or innocence. And now we're all set, because we know that Z is a Bernoulli variable. It's got a probability theta of success, a probability 1 minus theta of failure. And S12 is a binomial variable with parameters 12, the number of trials, the number of jurors, and success probability P, the probability a juror makes an error. And so we simply, by additivity, accumulate binomial probabilities and write down an expression. The first term, the first sum, tells you the probability of making 5 or fewer juror errors. The second sum captures the probability of 7 or more juror errors in the two cases of guilt and innocence. Now, of course, we could expand out the binomial probabilities, the atomic probabilities, in terms of the binomial coefficients and so on. But that is not necessary for our purposes at this time. We could always go back and put in place the algebra at need. We could stop here and say, well, we've done the problem. It's done. This is, in fact, the answer. And we can numerically compute this. There's no argument. But a little bit of algebraic massaging allows us to put this into a nice and compact form, which also has got a certain amount of intuition baked in. And to do this, we're going to try to merge the two sums together. So let's begin by looking at the binomial probabilities in the second summand. B12 of K and P, the probability that in 12 tosses of a coin with success probability P, one gets K successes. Now, let's write down the binomial formulation for this. What does it say? So the binomial probability is going to be given by 12 choose K times success probability P to the power K times failure probability 1 minus P to the power 12 minus K. Let's do a little bit of massaging first. First to the binomial coefficient, and then the two terms of the product adjacent to it. Now, selecting K from 12 is exactly the same as selecting 12 minus K from 12. The moment one selects K, one leaves aside 12 minus K. It is equivalent to specifying that 12 minus K. And therefore, we have two versions of the same binomial coefficient. They're both completely equivalent to each other. And let us play the following little apparently trivial game. Exchange the order of the two terms in the product, P to the K and 1 minus P to the power 12 minus K, as I've shown you. Now, it looks like I haven't done very much. But an examination of the expression on the right shows us that we've got another binomial formulation. This is the binomial probability that in 12 tosses of a coin whose success probability is 1 minus P, that one attains exactly 12 minus K successes. And therefore, we identify this exactly with B12 of 12 minus k with a success probability of 1 minus p. All this took was a rearrangement of terms, and we have this beautiful little symmetry. Let's rewrite our expression now using this identity. And so now we've got a first term and a second term in terms of the binomial probabilities evaluated at 12 minus k and a success probability of 1 minus p. Let's take a good hard look at the second sum. K runs from 7 through 12. As k runs from 7 through 12, 12 minus k runs between 0 and 5. And so if we replace 12 minus k by k, then it is equivalent to asking k to run from 0 through 5. And so we could simply rewrite the sum as follows. A sum k running from 0 through 5 of the binomial probabilities of corresponding to 12 tosses of a coin evaluated at k and success probability 1 minus p. Right. So all we've done is a completely transparent thing here. Replace 12 minus k by k. And then when k was in the original sum was running from 7 through 12, in the new sum k would run from 0 through 5. That is all it would say. Nothing has changed in the sum. But now, of course, the two sums on the right are running over exactly the same range. Addition is associated. We can do it in any order we like. Let's pull the terms together and pull the summation out and put everything else in square brackets in the middle. And there you go. A nice and simple and compact expression. Having done the work, we should see if there's any intuition here, whether there's some reason to believe it. And indeed, of course, there is. The term in the square brackets connotes exactly the probability that the defendant is convicted when the dissenting minority has got exactly k votes, k running from 0 through 5. Of course, this means that the majority has got 12 minus k of at least 7 votes to convict. Here's a nice and simple and clean, compact expression. Of course, one can numerically evaluate this if one knew theta and p. But let's hold on to that for a moment and move to the next question. So this is one step in our road. The deeper question, of course, is the question of errors. We come to that next.